In this lesson, we will be looking at permutations, combinations, and the binomial theorem. In this lesson, we're going to begin investigating the binomial theorem.
Okay, well, it turns out one of the more interesting applications of combinations is called binomial expansion. Okay, we call this binomial theorem part 1 here, but we're looking at binomial expansion. So we're taking something that's a binomial. Let me zoom in. Whoops, wrong way. Let me zoom in on this. Whoops. Sorry about that. So we're going to expand x plus y to the n. And we're going to throw any kind of any integer exponent, well, sorry, not integer exponent, but any positive integer exponent we want on there, and take a look at how we would do this. Now, it's okay when you're squaring this, you would just multiply x plus y times x plus y, and you would distribute that through. But if that exponent there, n, is larger, then that becomes a really onerous task. But it turns out there's some patterns here. Now, take a quick look at this. Okay, x plus y to the 0 is just going to be 1. X plus y to the 1 is just x plus y. Okay, there's nothing special coming out of that. And even this one right here, x plus y squared, you've seen this before. Now, x plus y cubed. Now we're starting to get a bit of a pattern here, okay? So notice what's going on here. The exponent over here was 1, or it looked like the exponent here was 0. The degree of this term is 0. The exponent on this binomial is 1. The degree for every term here is 1. The exponent here is 2. The degree on every term here is 2. The exponent here is 3. The degree of every term here is 3. If you add up the exponents on every single term, on the variables in every single term, they add up to 3. Now notice what happens with the x-coordinate here, which is, by the way, in this particular case here, the first term in all of these binomials. Notice where the exponent starts here. It starts at 3, goes to 2, 1, and then because it's not here, we assume this is x to the 0, or just 1. Look at this. And it's x plus y to the 4. This is 4, 3, 2, 1, and then it goes away. That's pretty neat. Notice what happens with the y, which is the second term in these binomials here. Okay? You don't really see it in this first one, but here, notice there's no y here. Y to the 1, y squared. No y, which would be like y to the 0, y to the 1, squared, cubed. No y, so y to the 0, y to the 1, squared, cubed to the 4th. So we've got these decreasing exponents and increasing exponents depending on which term in the expansion you're working at here. So that's a great pattern. Really, really easy to apply. Turns out there's another pattern that exists inside here in terms of the coefficients. We're going to talk about that in just a second here. First of all, I want you to notice here that there's, when we talk about binomial theorem, binomial expansion, there's kind of two different things that we talk about, and they're not exactly the same. The reference is not exactly the same, but we're talking about very, very similar ideas. When we talk about row 1 in the expansion here, we're talking about expanding a binomial where n is equal to 0. Row 2 of this, basically what we're identifying is the triangle. We've got this triangle that's kind of growing here. Row 2 refers to the binomial that has 1 as the exponent. Row 3 is going to have the binomial with 2 as the exponent. Row 4 is going to be cubed. Row 5 is to the 4th, and so on. So just bear in mind that when we number the rows, when we count the rows, the exponent is always offset by 1 because the exponents here start at 0. So let's take a quick look at this this little part right here where we're going to fill in the blank here. So the row is blank higher than the exponent. Well, we just saw that. The row is 1 higher than the exponent. Whatever the exponent is, that's referring to the row in the triangle here is always going to be 1 higher than that because of the way we count. We start counting at 1, but the exponent starts at 0. The number of the terms in the expansion is always, oh, now this is interesting. We didn't actually look at this, but it makes sense, is always going to be 1 higher than the exponent. Now just take a quick look at this. X plus y to the 5. Now bear in mind that there's no y here because this was y to the 0, and then it was to the 1, 2, 3, 4, 5. So because there's always a term that refers to one of these terms here being to the power of 0, to the exponent 0, the number of terms here is always 1 more than the exponent. So there's 1, 2, 3, 4, 5, 6 terms in the expansion when it's x plus y to the 5th. When it's x plus y to the 4th, there's 1, 2, 3, 4, 5. There's always 1 more term okay, than the exponent on that binomial. The sum of the exponents of the x and the y term in each case is going to be n. Okay, the degree, and we saw that before. The exponents of the x decrease term by term from n to 0, we saw that, and the exponents of y increase term by term from 0 to n. Now, if that wasn't cool enough, watch this. If you pull all the coefficients out of every term here and lay them out in their own array, you get something that we call Pascal's triangle here. Now, Pascal's triangle's got a really neat little pattern to it all on its own here. Okay, 1, 1, 1, 1, 1. Okay, 1, 1, 1, 2, 1, 1, 3, 3, 1. But if you haven't seen it already, for some people it's immediately obvious. For others, it's not quite so obvious here. Notice that 2 is the sum of those two values. 3 is the sum of those two. 4 is the sum of those two. 6 is the sum of those two, and so on. So what we do is we start with 1, and then we put 1 on either side, on the end of either row here, 1 on either end, and then what happens is we're basically adding along the diagonal. You can even think of it like this here. This number here is 1 added to essentially 0. There's nothing out there. So we're always adding upward along the diagonal there. This 10 is from the 4 and the 6, and so on. And these become the coefficients of any particular row in Pascal's triangle. Now, there's a couple interesting things about this. Notice that the sum of any row in Pascal's triangle can be added by using 2 to the n. Okay, the sum of this row right here this is 2 to the 0. The sum here is going to be 2 to the 1. The sum here, 1 plus 2 plus 1 is 2 to the 4. 1 plus 3 plus 3 plus 1, that's 4 plus 4 is 8. Oh, sorry. I didn't mean 2 to the 4. I meant 2 squared, which is 4. This next one is going to be 2 cubed, and so on. Okay, so whatever that exponent was that goes with the binomial expansion, 2 to that exponent gives you the sum of the exponents. Now, if we're talking row number, you gotta think of this a little more carefully here. If I told you what's the sum of the values in, let's say, row 3, okay, well that corresponds to n being equal to 2. So you just got to remember that that's how that works, that there's a slight difference between the exponent and the row in that triangle here. But there's one other thing that's extremely interesting about binomial expansion, and that's this part right here. That Pascal's triangle is actually just an array of combinations. Okay, this is where n is equal to 0, n is equal to 1, n is equal to 2, and so on. And then what we do is we start at 0 and we make our choices up to the value of n for that row. So at the n equals 1 row, this is 1 choose 0, 1 choose 1. If we come down here where n is equal to 4, then it's 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. And those are all exactly the same as what we're getting up here. So, and remember, when I say n, I'm talking about x plus y to the n. It's the same n. So down here, with 5 choose 0, 5 choose 1, 5 choose 2, these are all going to be the coefficients of x plus y to the 5. Like it's just an amazing pattern that shows up in Pascal's triangle here in binomial expansion that makes it so easy to expand even what would normally be really, really large expressions here. So now, what we're going to do here is we're going to start to apply these patterns, and we'll do some examples here, and you'll see how really quick and easy this could be.
Expand the following. X plus y to the 7th.
So it's an interesting thing here. Look at this, x plus y to the 7th. That would take a long time if you wrote those all out and tried to distribute that through. That's why we don't want to do that. But we've already seen enough here that we know what the pattern is supposed to be. So if it's x plus y to the 7th, as I've indicated before, if you know it's 7 here, then we know what the coefficients are going to be. They're going to be from that 8th row of Pascal's triangle, and that's going to be that in that combination, that's going to be, the coefficients will be 7 choose 0, and then 7 choose 1, 7 choose 2, and so on. 7 choose 3, 7 choose 4, 7 choose 5, 7 choose 6, and then 7 choose 7. Okay, so there's all of my coefficients. Then I know that the x, the first term in this binomial expansion, is going to start with the exponent 7, and it's going to drop down. So 6, 5, 4, 3, 2, 1, and then it's going to go x to the 0. So I'm not going to write that because it'll just be 1. And then the y, well, this is going to start at 0, so this will be y to the 0. So 1 plus, and this will be y to the 1 plus y squared. This will be y cubed, y to the 4th, y to the 5th, y to the 6th, and then y to the 7th. Now, interesting thing here, notice at every step along the way that the exponent on the y is the same as the combination that I'm making here. Y to the 6th, 7 choose 6. This is y to the 5th, 7 choose 5, and so on. Now, to finish this off here, what I'm actually going to do here is I'd like to figure out what those coefficients are. So I'm actually going to flip back to Pascal's triangle, what I've got down here. Okay, because remember how this worked here. This was n choose 0. This first one's n choose 0, n choose 1, n choose 2, n choose 3, n choose, sorry, not n choose. N is 0, n is 1, 2, 3, 4, 5. So here's 6. This will be 15, 20, 15, 6, and then 1. And then the coefficients for 7 will be 1, 7. This is going to be 21, 35, 35, 20, whoops, I don't know why I wrote a Z there, 21, whoops, you can't see that anymore, 7, and 1. So those are my coefficients. So now I can come back over here, and this is going to be 1, whoops, sorry, I'm getting so excited I forgot you couldn't see it. This will be 1 x to the 7th plus 7 x to the 6th y to the 1 plus, now that next one was 21 x to the 5th y squared plus 35, okay, x to the 4th y cubed, and I believe, I'm just going to check this again, yeah, 35 showed up twice there, it was 35, 35, so then we get 35 x cubed y to the 4th plus then 21 x squared y to the 5th plus 7 x y to the 6th plus 1 y to the 7th. Okay, we'll just zoom out a little bit here, and there we go. There's my expansion, and that's totally quicker than if I was to lay those all out and expand that by just distributing the multiplication.
2x minus 3 to the 4.
All right, now for this one here, it's the same sort of thing. Whoops, sorry, wrong way. Except that now we've got numbers in here where we had variables before. That's okay, we treat these things exactly the same until the very end here. So it's 2x minus 3 to the 4. That means my coefficients are going to come from the 5th row, and the array of combinations that correspond to the coefficients will be 4 choose 0, okay, 4 choose 1, 4 choose 2, 4 choose 3, and then finally 4 choose 4 way over there. Now, it's not just x at the first position here, it's 2x. But it's going to behave the same thing. This is going to be 2x to the 4th, and then it'll be 2x cubed, 2x squared, okay, 2x to the 1, and then 2x to the 0, which would just be 1. So even though it's a little bit more complicated than just x, it still behaves exactly the same way a variable all by itself would. The 3 here, now specifically the minus 3, okay, because I need to include the negative with that, that is taking the place of the y. So up front here, this would be negative 3 to the 0, which would just be 1. This will be negative 3 to the 1. This will be negative 3 squared, negative 3 cubed, and then negative 3 to the 4th. Okay, good. So now everything's there. Now I just have to evaluate it here. Now, when we talk about the 4th, sorry, in this case, my mistake, this is 5 here, so this would be the 5th row. of Pascal's triangle with its combinations of 4, the coefficients here are going to be 1, 4, 6, 4, 1. Now, I could flip over to the other page here and just look at the Pascal's triangle, but experience tells me that that's what that's going to be. That's not being clever. That's just remembering it after having done it over and over again. Now, 2x to the fourth. 2x to the fourth is going to be 2 to the fourth, or 16x to the fourth. Okay, that 4 will distribute through here. Plus, this is going to be 2x cubed will be 8x cubed. And then we're going to, then we're going to multiply by negative 3 to the 1. Okay, because we'll do that in a bit here. This will be 6. 2x squared will be 4x squared. Negative 3 squared is going to be positive 9. Then we've got 2x to the 1. This will just be 2x. Negative 3 cubed will be negative 27. And then out here, it's just negative 3 to the fourth, which will be positive 81. Not quite there yet, but almost there. So that first term is just going to be now the coefficient multiplied by that, so 16x to the fourth. Okay, done. Now, this is going to become, it's going to get a little bit more complicated here. This is going to be 4 times 8 times negative 3, so this will be negative 96x cubed. Then we're going to get, for this next one here, 6 times 4 times 9, okay, which is going to be 216 x squared. Then we're going to have 4 times 2 times negative 27 there. Okay, so negative 27, just doing this on my calculator. Now here we get negative 216 x to the 1. And then here we've got 1 times 81, which is just going to be 81. And so there we go. That's how you do it. So the first step there, you're just going to treat it as if this was just x and this was y here. But remember, the negative's got to go in there with it. You throw the exponents on top there, and then in the next row we start to evaluate and start to plug in those coefficients, and then we put them all together. Much quicker than doing the overall expansion.
A squared minus 1 over a to the 3.
Okay, now this one. Don't let this one throw you off with all the a's in here. You just approach it the way you would anything else, as if this was an x and a y here, x plus y here. So first of all, notice that it's cubed, which means we're talking about the fourth row of Pascal's triangle. This is the list of combinations of 3. So this will be, first coefficient will be 3 choose 0, and then 3 choose 1, 3 choose 2, 3 choose 3. Good. Then it's going to be that first term. Okay, and this is just going to behave like the x all by itself did. This will be a squared cubed, a squared squared, a squared to the 1, and then a squared to the 0, which is just 1. I'm not going to write it. Here, this will be negative 1 over a, because I got to bring the negative into this. Okay, so my y here is essentially negative 1 over a. So the first term will be to the 0, so it's just going to be 1, so I won't write it. But this next one will be negative 1 over a to the 1. Over here, this will be negative 1 over a squared. And this will be negative 1 over a cubed. Okay, now I'm going to throw down the coefficients. And when you're talking about these combinations of 3, 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1. So those are my coefficients. Then I get a squared cubed. Okay, a squared cubed is going to be a to the 6th. You just multiply those exponents there. Then I'm going to get a squared squared, which will be a to the 4th. And then I've still got this negative 1 over a. And I'll deal with that in just a second here. Then I'm going to have a squared to the 1, which will just be a squared. But now I'm going to get negative 1 over a, negative 1 over a squared, which will become positive 1 over a squared. Plus, and then back here, this will become negative 1 over a cubed. Okay, so now I've got the pieces there. Now I'm going to put them all together. The first term, well, that worked out beautifully. It's just going to be a to the 6th. Plus, and actually, I don't know why I wrote plus. I know that that's negative. I can see the negative. Positive times that negative will become negative here. Now, this is going to be 3a to the 4th divided by a. We'll cancel one of the a's and we'll get 3a cubed. Here, now notice what happens here. This is really interesting. positive. I've got a squared divided by a squared. Here's my constant term. Right here in the middle, constant. Now, in a lot of cases, the constant usually is the one that's trailing off at the end here, but in this case, it's embedded inside this set of terms here. That's the one that has no x in it. That's kind of interesting. Kind of like that. And then at the end here, there's nothing to cancel out with the a cubed in the denominator, so this simply becomes negative 1 over a cubed when you expand that out. So there's my overall expansion of a squared minus 1 over a, all cubed. Like that.
The binomial theorem.
So now we're just going to summarize this in the thing called the binomial theorem. And this is what it says here, that if you've got x plus y all to the n, that is the same as n choose 0, x to the n, plus n choose 1, okay, x to the n minus 1. So as this value here goes up by 1, we're subtracting 1 from the exponent on the x, but the y coordinate goes up to 1. This is y to the 1. When it's n choose 2, the x coordinate goes down by 2, and the y coordinate increases to 2. So it's the same thing there. And so on and so forth, okay? Until we get to the end where the x term there, the x factor there disappears because it's going to be x to the 0. We've got n choose n, y to the n. Okay? And so again, here's an example, and we've already been doing this. Okay? We had already been doing this because we saw that the coefficients were sets of combinations here. Okay, so here's an example of x plus y to the 6th without it being evaluated. But we can do a little bit better than that because we can see this little pattern here. Okay, it's a little bit more clear here, where this is n choose 2, and then we get x to the n minus 2. So it's the exponent minus 2. Oh, look at that, same number there. Y to the 2. Oh, looky, it's the same number. On this term right here, this is the 4th term. Now, and watch this, because this is the 1st term. That value there is 0. This is the 2nd term. The value is 1. This is the 3rd term. That value is 2. This is the 4th term. That little value down there is 3. And in the 4th term, notice it's n choose 3, x to the exponent minus 3, y cubed. There's a beautiful little pattern here, and it gets summarized in this expression right here. Okay, so in the expression above here, when we had 6 choose 2, x to the 6 minus 2, y to the squared, and that was our 3rd term here. Notice that what we're doing here is we're going to introduce a variable here, k. Now we already know that the exponent is going to be n. Okay, the exponent on the binomial, that's our n, and that's going to be the value right there. So the 3rd term in this case here is going to be the exponent choose 2. Okay, that's what we call the k value. And then it's going to be x to the 6 minus 2, or n minus 2, and then y to the 2 here. In general, we write it like this. This is t sub k plus 1. Okay, because if you look up here, notice that the term number, first term, was always larger than than the value that we're finding the combination of there. Okay, so n choose 0 was the first term, n choose 1 was the 2nd term, and so on. Okay, so t sub k plus 1 is going to equal n choose k, x to the n minus k, y to the k. And so this is an expression that we can use to help us find specific terms in an expansion without having to go through and do the whole thing here. Now, when we do questions like this, essentially any question that's going to look like the examples that follow here basically boils down to the question here, what is k? Because as soon as you've established what k is for whatever particular term you're looking for, then you know how to get the answer. From that point on, it's just filling in the pieces. So I'll show you some examples so you can see what I'm talking about.
Find the 4th term of the expansion of x plus y to the 9.
Okay, so when we refer to the 4th term, think of it like this. We're going to use t to refer to the term here. The 4th term would be t sub 4. Now, bearing in mind that this is supposed to be, according to our equation, our expression there, equation, t sub k plus 1, if we're looking for the 4th term, and these little subscripts here are supposed to be the same, that means 4 is equal to k plus 1. Ah, k is equal to 3. Okay, that makes this a lot easier for me to work with because now I know that. Now in this expression here, I also know that n is equal to 9 because that's the exponent on the binomial here. So now this is just a matter of plugging stuff in. I know that t sub 3 plus 1 is going to equal 9 choose 3, x to the 9 minus 3, y to the 3. Okay, because this is my k. Here's my n in those two positions, and there is my k in those three positions. Now, I just got to go to my calculator here and quickly evaluate what 9 choose 3 is, and it's going to be 84. And then this will be 84 times, well, this will be x to the 6th, and there's nothing to simplify there, y cubed. So there's the fourth term in the expansion, and I didn't have to go through the process of expanding it.
Find the third term of the expansion of 2x minus 3 to the 5.
Okay, so in this case, we're looking for the third term. So again, t and sub 3. The subscript there always identifies which term in the sequence. And again, if this is supposed to be t sub k plus 1, okay, it should be clear then that it has to be the case that k is equal to 2. Now, I know that k is 2, which is excellent because now everything falls into place here. I can also see that my n is going to be 5. So now, t sub 2 plus 1, my third term, is going to be 5 choose k, 5 choose 2. Now in this case, the first term here, x, is a little bit more complicated. It's not just x, it's 2x. So this will be 2x to the n minus k, 5 minus 2. And then instead of a y there, it's now negative 3. So it'll be negative 3 to the k, which in this case is 2. So now I just have to go through the process of evaluating the pieces. Okay, 5 choose 2 is going to be 10. Now, 5 minus 2 is 3. And that exponent, that cube there, distributes to both of the factors here. So this is going to be 2 cubed, or 8, x cubed. And then negative 3 squared is going to end up being positive 9. Now, I'm still not quite at the answer yet because I've still got values here that are being multiplied together that I can still simplify. And altogether, this will end up being 720 x cubed. And so that's the third term of the expansion of 2x minus 3 to the 5th.
Find the last term of the expansion of a minus 2b squared all to the 6th.
Now in this case here, to figure out what the last term is, again, my goal here is to get k. I got to look at the exponent here. N is equal to 6. Now, this means that my k value for every term in the sequence, remember my k is this value that changes as I go from term to term in the sequence here. Okay, it's different for every term, but it starts at 0 and it ends at the last term here. So in this case here, if I want the last term in this expression, the assumption is that k starts at 0 and that it ends at n. So in this case, the intention of this question is that you would assume right away that k is equal to 6. So now we're looking at t sub 6 plus 1, there's my k plus 1, is going to equal 6 choose 6. The x value has been replaced by a, but that's all that's happened. So this is going to be a to the 6 minus 6. Okay, well that's significant. 6 minus 6 is 0, a to the 0 is 1. That's actually going to disappear. Then, instead of a y, I've got negative 2b squared. Oh, there's a lot going on there. So negative 2b squared. And this is going to be to the 6. There's my k value. Now I'm going to evaluate the pieces. 6 choose 6 is just 1. A to the 0 is just 1. Negative 2 to the 6 is going to be positive 64. And then b squared to the 6 is going to be b to the 12. So altogether, this is going to be 64 b to the 12. That will be the last term of this expansion.
Find the middle term of the expansion of 3x plus 4y all to the 4th.
Okay, when the question asks for the middle term, again, the intention here is that you're still looking for k. But it makes it a little bit more difficult here. Now, so to have a middle term here, we got to really know how many terms there are in the expansion. Well, notice in this case that n is equal to 5. Okay, I'm sorry. I can see that n is not 5. Okay, I haven't lost my mind here. N is 4. But what that means is therefore we've got 5 terms. Okay, because remember how the terms start. K starts at 0, okay, on the first term, and then goes 1, 2, 3, 4 up to n here. So that's 5 terms here. So now, if you've got 5 objects here, 1, 2, 3, 4, 5, which one of those is the middle term? The third term. Okay, so this question is looking for the third term. Now, understanding that our notation here tells us that we're really looking for k, the k plus 1th term. If we're looking for the third term, that means, therefore, that k is equal to 2. So now we've got everything we need. We know that n is 4, and we're looking for the term where k is equal to 2. So now we can go to our expression here. T sub 2 plus 1 is going to equal 4 choose 2. Instead of x, I've got 3x, so this becomes 3x to the 4 minus 2. And then instead of just y, it's 4y. So this becomes 4y to the 2, to the squared there, okay? So there again, 2 is my k value, 4 is my n value. 4 choose 2 is 6. And then we've got, well, okay, 4 minus 2 is 2, so 3x squared will be 9x squared. And then we're going to have 4y all squared, so that's going to be 16y squared. So now we just have to multiply those coefficients together, okay, and we get a fairly large coefficient, 864 x squared y squared. So that's the middle term of this expansion.
Find the fourth term of the expansion of x minus 1 over x all to the fourth.
All right, finding the fourth term of the expansion. Now the only thing that makes this question different than the previous ones is notice that the two terms in there, x and 1 over x. Now, in every one of these expansions here, we end up multiplying this term by this term, so, or I should say a power of this term multiplied by a power of this term. So in this case here, you should anticipate, well, there's going to be some canceling here, and that's what we're looking to investigate here. What happens with that kind of canceling? So we're looking for the fourth term, and again, if that's supposed to be t sub k plus 1, this means therefore that k is equal to 3. So we know what our k value is. We should be able to just fill in the blanks now. We can also see from the expression that n is equal to 4. So we are looking for the t sub 3 plus 1. And this is going to be 4 choose 3. And now in this case, the first term is x. So this is just business as usual. So x to the 4 minus 3. But the y is a little bit different now. Now it's negative 1 over x. So this will be negative 1 over x. Okay, to the k, in this case that's going to be cubed. Now, 4 choose 3 is going to be 4. X to the 4 minus 3, well 4 minus 3 is just 1, so it's just going to be x. But here we're going to get, well, negative 1 over x cubed will be negative 1 over x cubed. Because negative 1 cubed will just maintain that sign there, right? The odd exponent won't get rid of the negative. Now, I've got an x in the numerator and an x in the denominator. I got a negative out there, so this becomes negative 4 over x squared. Okay, so yeah, we do get a little bit of canceling here, just as we would have expected. So there we go. The fourth term in the expansion is negative 4 over x squared.